Hello. Hello. So, my name is Eugenio Perez, and I will present this first part of this presentation of vDPA live migration downtime improvements for networking device. I will do a brief introduction so we can build all the optimizations on top. This is the agenda. I will start with the very basic concepts like SRAB, what is live migration, what is the problem we have with vendor-specific VFs, migrating between different vendors, how vRTIO vDPA solves that problem. We'll show a very brief, very small demo. And right at the end, I will send how do we overcome the problems, okay, with the shadow VRQ. So first of all, I'm pretty sure you are very familiar with this scenario. It's a typical one with VF, NIC, network interface that is split in many virtual functions, and each virtual function is assigned to a different virtual machine. These virtual machines can run Linux, Windows, whatever. Each virtual function is totally independent, and we want to live migrate to different virtual function, ideally in different hosts. So live migration, again, is the process of moving the virtual machine between one host to another one. Guests must not realize that the world is totally changing. We need it's totally transparent for it, and it has many use cases like load balancing, maintenance, etc. How does it happen? So the typical steps, or the most important step, is to mark all the RAM memory as dirty. So it needs hypervisor nodes that it needs to send to the destination. Then start sending all the RAM until a given threshold, timeout, etc. is reached. If the guest or anything modifies that memory, we should mark it again as dirty. And after this threshold, we must stop totally the guest CPU, transfer all the RAM remaining, and then all the devices states, all the devices that the guest see, need to transfer that state, and then resume all the execution in the destination. Again, the guest is totally unaware of all of these. So the problem, as you might guess, in migrating between two different vendors, mainly the vendor driver, okay? The virtual machine needs to have its own vendor-specific driver. And if you migrate from one vendor to another, this is not going to work because the destination NIC has a different driver. Apart from that, the NIC must support, obviously, this kind of live migration, resuming, etc. Not all drivers support it. So this generates bytes coupling. How vRTIO solves that? Maybe many of you already know, but summary, vRTIO is just an application that describes how virtual device and virtual and guest drivers and how they interact between each other. Composed of a data plane, which carries the actual buffer. The data plane is composed of virt queues, implementing on virtual rings, vRings, the typical circular queue, and it transfers the actual buffers, the actual net buffers in the case of vRTIO net. And apart from that, it has the control plane. Control plane manages the data plane and describes how it works. For example, different features are able to optimize or to modify how this vRing and on top of that, vDPA. So vDPA is vRTIO data path acceleration, and basically tries to directly pass through the data plane, so you have the full hardware offloading performance, but emulate the control plane. So the vendor doesn't need to implement all of the vRTIO control plane in the hardware. Very convenient because it's not 100% treated for hardware. So physical NIC or the virtual function only needs to implement all that data plane, and vDPA framework in the Linux kernel is able to translate these control plane messages to vendor-specific messages. So with vDPA and vDPA, we are able to do all of that migration because the guest has only the virtual.net driver. So it's able to migrate, and then it's in the destination, and everybody is happy. In the demonstration, I will migrate from AMD ceilings NIC to an NVIDIA NIC. Demonstration is only a proof of concept. It is not tuned for performance or anything like that. And in the scenario, they are connected via a network switch. And we have another port which is running the Hyper server, so you can see that the migration keeps all the workload running. So this window, this pane is the source of the live migration. And you can see here the hardware it have. You see the Sailings NIC and the Melanos one. And in the destination, you can also see the corresponding NICs. You can find more details on this demo in the last year KVM forum, but I will not close on this. Here we start the source QEMU server here, top right, and the destination QEMU, which is just waiting for the source to send the virtual machine. We start here the workload, then start the migration, and now the migration is starting and is finished. Okay. So all the virtual machine was able to live migrate. It's a little bit fast, but you can find more details in the last year KVM forum. Okay. So, and you can find it here in YouTube also. So the main problem here is how do you track the memory that the device has modified? It's a little bit hard with vanilla PCI pass-through because the device is talking directly to the VM, not to the hypervisor. So what we do to be 100% generic is to add a shadow virtue. So when the virtual machine is migrating, it will not talk directly to the guest in the data plane, but it will talk with QEMU, and then QEMU will forward all the requests to the guest. That way, QEMU is able to track all the modified memory. We don't copy the descriptor in that sense. We don't copy the buffers content, sorry, or the net frames contents, only the descriptors. So to go from one configuration, let's say, to shadow virtue, from pass-through to shadow virtue, we first allocate the shadow rings. After that, we suspend the device. We get all the state that we need, for example, the index position, etc. So again, the guest totally unaware of this operation. After that, we configure the NIC to use the new virtual queues. And now the VF is running again. So when the guest makes more buffers available for the NIC to consume, QEMU will copy these descriptors here and will notify the device that new buffers are available. When the device has finished processing the descriptors, picks QEMU again, and then QEMU is able to notify the guest and to write out all the dirty memory to note, mark all of that as dirty, so it knows that it needs to resend it again. And
Hi, this is C-Way from Oracle. Yeah, to Eugenio's introduction. But I would like to talk about the use case that we have as a cloud service provider. We think that it's necessary to choose the best downtime for live migration. Yeah. Let's start with the requirements. So first is that scalability in cloud is really something that we want to address. And the other thing is performance. So with a lot of work in the past few years, we have been devoting a lot to actually try to extend or try to add more features to vDPA and try to make it feature parity. So the performance, I believe mostly will be able to satisfy our cloud requirement. And in terms of scalability, if you don't take line migration into account, so with a couple of vendors, it will be able to achieve the scalability requirement, like we want to support 100 virtual functions per card or even thousands. We want to support containers, and we want to support a high density of number of Linux for VM. It's also there's sort of a way that we can support that too, but the real problem or the real challenge is that once you put this scalability requirement into the line migration perspective, it looks like that we run into some bottleneck. We'll show that why it's just like this sort of problems. But the thing is that we want to be able to achieve the let you know that we want to be able at least have the IO performance still during migration. Like the minimum is like half percentage or 50% of the regular time without the line migration. And still we want to achieve because this involves the scenario where we want to migrate or want to move our customer with using the without PV drivers, that they can still use their PV drivers, but instead of using the host backend, they can actually use some hardware offloaded backend in the with the help of devices. So in that case, we want them to be more transparent with this process, and then they can actually not be able to notice the difference between the it's on the hardware, the substantial downtime that on their migration use cases. So the goal here is to have taking this to account in the number of actually in the subsequent latency of the per VM, and you want to take account of the number of Linux that you want to support. It's like to have like maybe from a dozen of Linux to a couple hundred. Things will become very complex. So the goal is to have like the per device, tear down or that sort of cost to be less than 100 milliseconds. So that's per device. And with parallelization, we can actually achieve a more, we'll be able to actually migrate Linux in a way that we want to have like one particular thread, to do the migration for each device. So that's the basically the requirement or the use case we want. We are looking forward to. Okay, so starting from last summer, that Jacob and Eugenio and I actually been discussing the possible way to do migration, possible to, not actually using software-based, or shadow overkill mechanism, or to just use the hardware assisted dirty checking. But that there's a lot of challenges, not just like us. The first thing is that you want to do dirty checking with the device, so there's a lot of complexity, or there's a lot of tracking over the memory gaps. And particularly in the case of migration, the kind of the pressure on the memory bus or the PCIe is pretty significant. Here we don't want to stress a lot with the devices. And the other thing is that scalability is also a concern when you want to support. So maybe it's working okay with like a couple devices, but if you want to extend to migrate like 10 Linux or maybe 30 Linux or maybe even 100. So that would be a problem. But the hardware has to have that capacity to actually not only to deal with the memory that you need to keep track of, and also you need to be highly contentious with those, the dirty checking process that's in the host. And the other challenge is that there's no way or there's no building mechanism in the device to actually throttle up down or up and down on the DMA activities. But this really is a requirement for us to actually be able to throttle it down. So eventually we had to resort to, slower mechanism like the hypervisor to actually kick in to actually block the vCPU execution from being stabilized with the gas workload or things like that. So we don't really want to, build a mechanism like that. It's easy to start, but it's hard to optimize in the future. So I guess most likely the hardware device is not invented that way, because hardware device that we are looking here is like to do the most motivations doing the I/O, not doing trying to be a way to actually compete with the whole CPU or with the speed of the whole CPU processing. So with that regard, I think the future direction or the future that we are looking to is to have the IOM UFD dirty checking. So it will be more permitting than to utilize the hardware device to do the dirty checking. Yeah, but the reality is that these IOM UFD dirty checking is only available in newer platforms. But we really want to take a solid first step to have sort of like a workable solution first, because that will be give a more coverage about having to depend on some specific platforms or a few NICs that only has that capacity or has the most advanced support for migration. Yeah. So that explains why do we want to stick with shadow workflow first to have that. And we look back and then see, okay, is a possibility to actually enhance that? I think that is quite possible. And basically, I think the first thing is that as background, it's not always to actually ask the vendor to fix the devices and come up with the sort of acceleration. It's not easy to do that way. But instead, we can look at lower mitigations that we can actually try to bypass those, hardware slow paths, or those, we ran different kinds of benchmarks and provide those, different contribution to those, downtime. And we identify those bottlenecks, and we found that okay, the major bottleneck that we showing in the profiling data is that it comes from the memory pinning and mapping, and I guess that's common to every devices, and because if you're trying to dealing with the from the hardware perspective, you need to deal with DMA, so that's the common part that we can actually easily get rid of, in the first place. So this will really help to drive the reduction down to like a few seconds of the downtime. So it's really significant, improvement that we can take advantage of first. So that only involves the QEMU changes or the hypervisor changes. It doesn't need to involve any driver optimization. But after that, I think most of the part is on those hardware slow paths, and we take NVIDIA Malus devices to analyze those possible bottlenecks, and then identify each of them, and we identify some bottlenecks with regard to mapping or how it deal with the creation of the work queues that in the downtime path. And we try to, come up with different ways to try to bypass or mitigate with either, moving ahead or to just bypass or just, and do some pre-creation. And besides that, there's also some generic aspect with regard to the spec required plumbing with regard to vHost vDPA, because it starts with the software implementation in the first place. Is sort of, because if you want to make it run not only on the hardware backend, you want to also make it work on the software backend. You need to start with, software first, right? Because that's easy to emulate and that's easy to, do your own work. Yeah, but on top of that, we can actually look into the ways to enhance that on hardware devices. Yeah. So this summarizes a couple of philosophy that we follow. So the first thing is that we can actually make, the most common way is that the device reset is really quite slow for a lot of hardware devices. We come up with the suspend resume with really relatively lightweight mechanism. Actually try to suspend the device and as much as possible with a lot of device, save in the device and resume it as is, so that we can take advantage of that without having to reset device and then doing everything and recover the state, doing over again. And the other thing is about the mapping cost. That's not only pinning, there's also mapping cost in some of the, it's really generic to not on the on-chip IMU providers, but on those, which have to depend on the platform IMU. So we have sort of, kind of a discussion whether we want to take like generic approach to actually fix the DMA API for the vDPA subsystem, or we want to, use some, device dependent to do that. So the device dependent means that on the IOMU chip providers, we can come up with the dedicated address space to host those shadow work queue descriptors. So there's no need that you need to have to involve with the a lot of translation in the shadow work queue, and that works the best on the Manus device because it has its own IMU. But we have to think about how to extend it to like the platform IMU devices or devices who have to use the platform IMU. I thought that we have couple, ways to do that, but it really needs your input on that part. And the other thing is the destination. There's a sort of latency because driver we really need to bring up the data plane. So that will involve the a lot of hardware slow path on that part. So it's the takeaway is that we can either move ahead to device initialization if that's also possible, but if not possible, we can actually doing some VMU level enhancement to do to make it part of the pre-copy phase. While in the you prepare the migration on the destination, where you can actually try to synchronize the state and try to amortize those device setup costs on the destination. Once you move it, and then it will just come up with as is with what you have on the source. Yeah, that will be backed up by the vHost vDPA backend features that those device specific optimizations. So if you have your specific bottlenecks on those downtime, and you can add your own backend features to actually get your device enhanced or optimized for those downtime requirements. And besides of that, there are a couple ways that we can try to improve that. from the QEMU or hypervisor perspective. So with regard to programming of the control plane, it's now required to go through the controller queue ioctls. So we are thinking whether we can actually streamline this process so that basically right now if you have a extensive number of queues, you need to apply those control methods to each queue. But yeah, maybe we can actually streamline that with one single shot of message with our ring or sort of interface that from the user space from the QEMU to the kernel to actually try to batch that or make it more synchronous, and that way that we can actually have better way to or leeway to so far this is not a problem for us, but just in case we have a large bunch of devices to carry out and it turns out to be the downtime bottleneck, we can go with that organization. And also we can actually leverage the parallelization with multi-threaded, provide tier down or sub, so that we can just use multi-FD in the QEMU process to do that. Yeah, so this really needs your help as vendors to actually give more input. So maybe we can actually generate some of the mechanism and or come up with better, design or better way to do the implementation. Yeah. So with regard to all those enhancements, I think that we can give like a satisfied result with regard to downtime, because all of those possible bottlenecks due to the hardware has been eliminated. And but another aspect with regard to the I/O performance for shuttleable queue, right? And we still have some sort of plan to enhance that, because in theory, it just need to forward those or rewrite this to metadata rather than copy the memory. So basically, it's a zero memory copy case that we can actually enhance that with techniques like using multi-threaded, or we can actually resort to the pack ring support, get better cache utilization and less PCIe transaction pressures. And this, I want to point out, and the last I want to point out that this, shuttleable queue is also useful to in a lot of scenarios, because right now it's very hard to actually implement legacy support on the with the pre-spec, pre-spec meaning that it's a pre-Windows spec, but with the help of shuttleable queue, it's not hard to do that, because once you got sort of whatever spec is backhand devices, you can actually leverage that up, because you just to forward the legacy layout and translate into the window of compliant layout. So that will be able to help us to eventually achieve the device emulation for the legacy support with the help of the modern devices. Yeah, that summarizes all the possibilities that we are looking to in near future, and we hope that we can get more feedback from you guys, so that either data that actually what is the bottleneck, and you can collaborate. Okay, so the rest time will go to Vegas, because anyone who is doing the rework for the kernel and driver perspective. Yeah. So
how much time do we have left? How much time do I have? Hello? Can you hear me?
or at 40, I guess. Yeah. We started at 40, so I guess maybe there will be 7 minutes.
How much? 7 minutes? Okay, so that I know.
7 minutes.
All right. Hello, everyone. My name is Dragoș Setula. I'm from NVIDIA. So we're going to go through the improvements that were made for vDPA lab migration downtime. So let's quickly define what downtime means, or the two downtimes. There's the first downtime, which is basically at the start of live migration when the shadow work queues are reconfigured and then they are started. Then you have the live part of live migration. And then finally, on the source side, we stop the devices, and then we do the rest of the migration, let's say, during the downtime 2, which is not really migration, it's configuring the device on the destination side. And as we will see, there's a lot of configuration happening. So let's take like a tracing view. You have on the upper side like a QEMU source VM, on the lower side the destination VM. So there's a migration with two devices on the same host for timing principle to have the same timeline easily. So we have here, you see, we spent some time here during downtime 1 to do the shadow worker configuration for two devices. Then some time spent on the source, not so much, on downtime 2. And then a lot of time spent on the destination VM. This is the page pinning that Siwei was mentioning. So let's have a closer look. What we have here is on the source, we have a lot of memory mapping operations. They can be costly for large VMs. And furthermore, we have many of them. So we have a lot of mappings and flushes, which mean unmappings. And besides that, which is not so visible in this flame graph, I think it's somewhere like here, it's the cost of tearing down and setting up hardware work queues. On the other side, on the second downtime, we have this huge cost here, which is the page pinning. Then there's also a bit of mapping, but it's mostly page pinning and some queue creation and configuration operations. So this is with the focus on the NVIDIA device, of course. This is how the optimizations were made. Not all of them, but some of them. So one note, we have, like, there are two things that are slow. Creating memory mappings for very large VMs. By large, I mean lots of RAM. So we have our own on-chip IOMMU, and when you send the mappings to the vDPA device, then, yeah, it takes some... It can be up to hundreds of milliseconds to program. Even it used to be like a second if they're really, really large. And furthermore, you have to delete the old mapping, which also takes some time. And then the hardware work queue creation and deletion is not as expensive, but when you have many devices with many work queues, it adds up, as we will see. So this is like Performance 101, how to improve, basically do less or do not at all or do faster. Easy. So now we can jump into the improvements. These were mentioned partially by Siwei as well. So we're going to take them one by one, and then we're going to see the numbers. So on the first one, this was the large cost that you saw in downtime 2. So the page pinning that happens on the destination used to happen during downtime. And the observation from Eugenio, I think it was that we already know the layout of the source VM when the live migration starts. So we can send the state of this of the layout during the live part of live migration. And so you basically, that also means that you have to keep the migration going until these things are sent as well. That's not a problem. So you send them and you do the mappings before, and then you save. You will see a lot of time has been saved. Mapping has been moved to a separate thread to not block the command interface. And so this patch is only in QEMU. It has been, so it's generic. I think it's going to get merged soon, if I understand correctly. It doesn't seem to be merged yet. So going to the next one. This is a more like device-specific thing, but the change was in all levels of the stack. So from QEMU, kernel, and hardware. The idea is to have a separate mapping that contains only the descriptors for the shadow work queues and the control work queue, and program this descriptor, this mapping with the descriptors into the hardware work queues. The hardware work queues now have support for this. So the idea is during normal operations, that mapping is the same as the large VM mapping that you normally put in. But during live migration, we switch that over to the smaller mapping that we pre-create. So this involves a new API for configuring this mapping into its own PCI address space ID. And yeah, on the kernel side, the changes were accepted. On the QEMU side, they're still pending. Then we have the decoupling of that, so making basically of the device reset, so removing memory flush, an extra memory flush from the device reset. This has been accepted at 6.7. Resumable work queues already mentioned by Seaway. We basically don't have to recreate queues anymore. We just configure and resume them, which is a fast operation. This was accepted in the kernel, and on the QEMU side, it's still you have a link there to the branch. It's going to be upstream once the other changes are in. Then pre-creation of hardware work queues. This is on the destination side, where we basically create them and at vDPA device add time, and we save some additional hundreds of milliseconds per device. So let's look at this is the interesting part for the numbers. So we have here a VM with 128 gigs of RAM, 8 CPUs, 2 vDPA devices with 4 data work queues, so not so many. So using the numbers are taken with Migmon. Initially, you see here, so this is the page pinning cost of the division, which disappears in the second column. You see that there's no more. It's a big improvement already. Then you see another improvement once all these were kind of in the same batch, so I don't have separate numbers. A big improvement on the destination side, because that was the focus. And once more with the resumable VQs, there's another improvement on the destination side. And with the VQ pre-creation, we have for a larger setup, 256 gigs of RAM, 4 devices, 32 word queues, we have like a 300 millisecond per device reduction. And then for upcoming improvements, so Seaway mentioned this, we have like parallel device operations from the QEMU side, driven by the QEMU side, parallel VQ operations, this is work in progress, where we parallelize the VQ suspend and resume, also the memory mapping creation and deletion. And then there's more potential work to be done to take things out of the destination downtime. So I hope it's a bit more than 7 minutes, but I tried to sprint. Any questions? Or handing it back over to Seaway and Eugenio.
What was the downtime number? Sorry, I didn't catch that.
So initially,
the final downtime number.
Well, you can see
which one?
The final downtime is like 1 second or thing. Yeah, I think there's some remaining work that's needed from the QM side to actually try to batch the memory mapping. I think that's why that is shows up as like
this
1.3 seconds, for the downtime number.
The numbers are in seconds down there.
Yeah, but
the number in seconds.